Oh, yep, I don't see nothing there.
I was able to
Or maybe
find them.
maybe it's still loading.
It looked like they all went in.
Oh, yep. I think it just takes a second to load because it's a web page trying to load like assumedly hour-long videos.
Yeah.
Okay. Yep, I see them. Okay.
So that everything that will be on the exam should be in the lectures there. Yeah. So I covered rotations last time.
Okay. Gotcha.
All right. So what I want to start with today. When we wrote down the rotations last time, we defined the infinitesimal rotation operator r hat z d phi. We defined that as the unit operator 1 minus I over h bar times jz hat, where this was it's essentially just the sz operator times d phi.
Okay.
Yeah.
Okay, so what is that? I can't quite read.
That's the unit matrix 1.
Okay.
Because this is a matrix, jz is sz, it's a 2 by 2 matrix.
Okay.
So that's a 2 by 2 identity matrix.
Gotcha,
okay. Okay, so this, when we're going to define other operators that have this infinitesimal form, and they're all going to be 1 minus I over h bar times some differential times some generator here, which is the jz in this particular case. So right now what I would like to do is just give another example of translation operators. Or the translation operator. And to motivate this, I just want to give a simple definition from the Taylor series expansion. So consider the Taylor expansion. If I have some function f of x, and I want the function at a nearby point, f of x plus a, well, that's the function at x plus all my correction terms, which will be a times f prime of x plus a squared over 2 factorial f double prime of x and so on, plus a cubed over 3 factorial f triple prime of x and so on, right? So I can write this as the sum over n equals 0 to infinity of a to the n over n factorial, and then f n of x, where this denotes the nth derivative of x. Okay, but what also remember that e to the x that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. So we recognize that from the Taylor expansion of a function, here we have an exponential, and in fact we can rewrite this as the sum n equals 0 to infinity of a to the n over n factorial, and then d by dx to the n, where this whole thing just operates on f of x. And so we can write f of x plus a is equal to, this is just the exponential function, this is just equal to e to the a d by dx operating on f of x. Okay, so you've probably never seen that before, an exponential with a derivative operator in it.
Well, I've seen integrals in the area, but not derivative.
Well, now you've seen derivative. So, okay, so let's rewrite this.
Wouldn't that just be like a differential equation with a logarithm though? Or can you not do that?
Well, you can't really do that because this thing is an operator and it has to operate on the function. So I can't take like the log of it.
And you can't take the derivative out of the exponential.
Right, yeah, you can't really do that. Okay, so let's just rewrite part of this. I want to write a d by dx. I want to write this as minus I times I. So that's minus I squared, that will give me 1. And then I want to put in a couple of h bars, a d by dx. So I can write this as minus I over h bar times I h bar d by dx, and then times a. And let me put the minus inside. Okay, so this we can write then as let's define p hats of x. I want that to be minus I h bar d by dx. We're going to just define this. So that means we have f at x plus a is equal to, so I can write this then as I over h bar p hat x times a. So we have e to the I over h bar a p hat x operating on f of x. Okay, and then I can write f of x minus a is equal to e to the minus I over h bar a p hat x operating on f of x. All right, so what we've accomplished here is we've written a way to translate the function f by a distance a. Okay? And so when we can translate it, this is this is translation to the right by a, and this is translation to the left by a. Okay, so this is left translation. And this is right translation. Okay, so let's look at, for an infinitesimal translation, dA, the translation operator, T of dA, will just be 1 minus, this is now just the expansion of the exponential function, 1 minus I over h bar dA times p hat x. So this is the translation operator. The differential translation, or differential translation. Okay, and p hat, what we've defined here, p hat x is the momentum in the x direction. And what we see here is that momentum is the generator of translations. Okay. So we saw that angular momentum was the generator of rotation, and now we see that momentum, linear momentum, is the generator of translations. Yeah.
Is that a lowercase p for momentum?
Yeah. Yes.
So is this left and right? Because you're like, I'm visualizing like an x-axis. Could you have this like with y values, z values, and it just mirrors in the other directions, right?
Yes.
Okay.
Other questions?
Am I supposed to understand how we got from the left and right translation definitions over there to that infinitesimal translation?
Yeah, if I make a infinitesimal,
Okay.
That's because it's a derivative, right?
then it's just 1 minus, if I do the expansion, so the expansion of this thing is e to the minus I over h bar a p hat x. The expansion of the exponential is just this thing.
Oh.
Right? So that's 1 minus I over h bar a p hat x, and then you'll have plus I squared a squared p hat x squared over h bar squared 2 factorial plus dot dot dot.
Yeah.
But if a is small, then I can just take the
Okay. I understand.
How do you define infinitesimal in quantum mechanics?
the same way you would classically. It's just an infinitesimal number. So dA is just dA is just an infinitesimal real number.
Okay, is there like a comparison between it and another number that has to be much larger than, or is it just, you just define it as approaching 0?
Approaching 0. Okay, so now let's look at, so we have a new operator. We have an operator piece of x, and it's the derivative of with respect to x. So let's calculate now the commutator between x hat and px hat. So x hat we didn't really talk a lot about yet. This is just x hat is the position operator. And it's represented as just as X. So we can calculate the commutator between X hat and piece of X hat. Okay? Now, before we just wrote down, this is of course what we wrote down before, which is just this. But that's really hard to figure out what it does. So the way that you calculate commutators is you put a function here and let it operate on the function, right? Because this thing is, piece of X is a differential operator. So if you want to calculate it correctly, put a function, a test function here, and let it operate on it. So we'll calculate X hat, P hat X operating on some function of X. And where this is the test function. So let's go ahead and write that out. Now we can go ahead and write out what this is. This will be X, P hat X acting on F of X minus P hat X times X F of X. Okay? I'm just letting these operators act on F. So this will be X, P hat now is minus I, H bar, d by dx operating on F of X. And then we'll have minus I, H bar, d by dx. And now this is a differential operator. It differentiates everything to the right. So it will operate on both X and F of X. Okay? And this is why you want to use a test function, because this is the way to get the right answer. So now we'll just have minus IH bar. This d by dx differentiates that F. So we'll have X F prime of X. And then here we'll have plus. This minus can come out here, IH bar. And then we'll have d by dx operating on the product. So the derivative, when it acts on X here, I'll just get F of X. And then plus X F prime of X. Okay, so now we can see that we get a cancellation. We have the X F primes go away, and so what we're left with is IH bar F of X. And so this is equal to that commutator of X hat P hat X on F of X. So now that I have this relationship here, I can just, the F of X is just, I can abstract that away or just take it out because both of these things are operating on the function. So this just says that X hat P X hat is equal to I H bar. Okay, and this is called the canonical commutation relation. And this is a very central, it's very central in quantum mechanics. Okay, are there any questions so far? Okay, so what's interesting about this relationship? In classical mechanics, the phase space is given by the set of coordinates x sub I, p sub I, for all the particles. Okay? You all remember phase space from classical mechanics?
I think I actually got it confused with Hilbert space. Second day, I was like, "Oh, is this like phase space?" And he said, "Nope, it's Hilbert space."
Who said that?
I asked about phase space, and then you.
Oh, that's right. Yeah, right. Yeah. Okay, so classically, xi pi equals pi xi. Okay, the coordinates in phase space commute. In classical. Okay, so in quantum mechanics they don't, and this has deep geometrical meaning. So the phase space coordinates in quantum mechanics don't. That changes the entire nature of the geometry of the manifold that describes, particles in quantum mechanics. Okay, so that's the big difference. That's the huge difference between. I mean, that is just the transition. The transition between quantum mechanics and classical mechanics is just this. You take the classical phase space, you make the coordinates non-commuting, and you have quantum mechanics. Okay, so let's look now. Let's go ahead and calculate the orbital angular momentum. So from we also have the relationships. We also have. Let's see if we have y hat. We also have this commutation relation between. Between P and Py and Z and Pz. Okay? So in quantum mechanics, Y doesn't commute with Py, but Y commutes with Px just fine. Okay? It's only the identical conjugate. We say that P is conjugate to Y here because that's what's non-commuting. Okay, so now let's look at orbital angular momentum. So for orbital angular momentum, we'll go back to the definition here of the definition that we know from classical mechanics. And if we calculate, so this is r plus p, this would be then, this would be x hat, y hat, p hat, and then p will be px, py, and pz. Does this look familiar, this construction of using the determinant to write this out?
Mm-hmm.
So then Lx, the Lx component here would be, y pz minus p, this is supposed to be z, minus z py. So okay, so that Lx is ypz minus zpy, and Ly will be xpz minus zpx. And then Lz will be xpy minus ypx. Oh wait, this has to be a minus there and a plus here. Right, following the rule from the determinant that this, when I do this component, I have to put a negative sign. So that would be, yeah, minus xpz plus cpx. Okay. Okay, so let's calculate the commutator Lx, Ly. Okay, so this is Lx, Ly minus Ly, Lx. And this will be, okay, so now Lx is y hat pz hat minus z hat py hat. Ly is z hat px hat minus x hat pz hat. And then I subtract off z hat px hat minus x hat pz hat times y hat pz hat minus z hat py hat. Okay, so now let's see we'll have some cancellations, but then we have to be careful. Because remember, this pz, for example, here contains the derivative with respect to z. So if it hits this term over here, remember it can differentiate that z, and so on. So let's just, we can write all this out. So this, let me drop the hats here just for the purpose of not having to write all of that. So this will be, we'll have ypz, zpx minus ypz, xpz. So we have to keep everything in order here because there's differential operators. Minus zpy, zpx plus zpy, xpz. That's the first set of stuff. And then minus, well, let me see if I can just do this without making a mistake. The first term will be, let's see, minus zpx, ypz. And then we'll have a plus zpx, zpy, and then let's see, I'll have then this minus will be a plus xpz, ypz, and then let's see, I'll have these two minuses give me a plus, and then I'll get a minus from there, it'll be xpz, zpy. Okay, so we've got these 8 terms, and these are all, so what are the terms well, there are certain terms here that there are no problems. The derivative with respect to z doesn't affect x. X is independent of that, so we can pull that out. So this will just be something like xy times pz squared. And the same thing here, px and pz can switch because x, the derivative with respect to x won't affect that z. Okay, so let's see, I should have terms that cancel, so we've got this pz squared with x and y. I can cancel this term and this term. And then we've got these z squareds with px and py. Now I can switch px and py because again, those derivatives don't interact with each other. They're not, totally fine. So this term can cancel that term. Let's see, do I have any other terms that I can cancel? This term here, let's see. I've got.
Is it x hitting the y? Y hitting x?
I've got py pz, py pz. Okay, but I'm differentiating pz here. I've got a pz operating on the z, so I can't pull this z out. Okay, and then I've got this term here, I've got px and pz, but then I've got the pz that's operating on the z here, so I can't cancel those. All right, so let's just see if we can, how can we rewrite this then? I want to be able to use these commutation relations here to solve it. So if we look at this term here, I've got this px, I can move all the way through to the other side here. This will be just ypx. So I can write this as ypx, and then I've got pz times, pz is first operating on z. And then this ypx I can also pull forward. And so then I've just got here a minus z pz. Okay. And then over here we've got plus, I've got x py, and then we've got a z pz. And now I'm subtracting off. Let's see, what do I have here? I've got an x and a py, again, but a pzz, so this is minus pzz. All right, so what do we have? We have this commutation relation with z and pz says that z pz minus pzz is equal to I h bar. So what I have here, I have just I have the negative of that, right? I have minus zpz plus. So this is just minus IH bar. And then here I have plus IH bar. So what do we have? We have IH bar, and then we have x py minus y px. Okay, but what's this? X py minus y px, that's just LZ. So this is IH bar LZ. Okay, so we have the following. So we have Lx, Ly is equal to IH bar Lz, and then we'll have Ly, if you copy it, Lz is equal to IH bar Lx, and then Lz Lx is equal to IH bar Ly. Okay, so these are the orbital. So the orbital angular momentum commutation relations are identical to the spin angular momentum. Commutation relations. Okay, and that's how you know that the electron has a spin angular momentum. That's how you know it's an angular momentum, because of that relation. Okay, so Sx, Sy equal IH bar, Sz, etc. is an angular momentum. Let me show you a way. I'll show you some notation that's it's very useful. Okay, so if I have epsilon, I, J, K, so it's a 3-index epsilon symbol, then this thing is, it's +1 for even permutations of I, J, and K. -1 for odd permutations. And it's 0 for other, and that means repeated indices or anything like that. Okay, so that means that if epsilon, so I, J, and K are in the set 1, 2, and 3, then that means epsilon 1, 2, 3 is equal to 1, which is equal to epsilon 3, 1, 2 equals epsilon 2, 3, 1. And then epsilon, if I take something like out of order, like I swap the 2 and the 3, so 1, 3, 2, that's equal to -1, and then any rotation of those. So epsilon 3, 2, 1 epsilon, let's see, is that right? Is that all of it? Oh, 2, 2, 1, 3. Okay, and then anything else is 0. So epsilon 1, 1, 2 equals 0, etc. Okay, so if we do that, then we can do the following. So for x equal 1, y equals 2, and z equals 3, we can write the relationship as follows. Li Lj is equal to I h bar epsilon ijk Lk, or in Si Sj equals I h bar epsilon ijk Sk. So you can write all three of these at the same time. And it's not just for notational convenience, it's also deeper than that, but anyway, it's a very nice way to be able to write things. Okay. Are there any questions? Okay. All right, now that we've seen some of these operators and these generators, we okay, let's I want to talk about the spin of the photon in just a moment, but in order to work that out, I want to talk about what happens if you have an operator that's in an exponent and you have it's operating on a state vector. So this is how do exponentials of operators act on eigenvectors. So let's just consider the operator A. And suppose it has an eigenvector little a, such that when it operates, it just brings out the eigenvalue. Of that eigenvector. Then what is, if we what is E to the, say, I over H bar, A hat operating on, if we operate with this operator in the exponent, and we operate on that state, what do we get? Okay, the way to think about this is, again, just use the expansion of the exponential. So e to the I over h bar a, that will be 1 plus I over h bar a plus 1 over 2 factorial times I over h bar a squared, and so on. Okay, so when this expansion, this is just now some big mess that's operating operates on A. So what do I get here in the, what's in the big parentheses here? After this operates on A, what do I get on the state vector A?
Get the eigenvalue. My guess is that you'd get the eigenvalue, but it's in, like, it's either in an exponential or it's times a coefficient of some sort.
Well, I mean, just for what's in parentheses here, what do I get after it operates on eigenvector A? What does 1 times the state vector give me?
The state vector.
Just the state vector, right? What does this term give me?
That gives you an eigenvalue.
Yeah, eigenvalue times I over.
Right, this just gets replaced with an A.
Yeah.
What about here?
A squared.
A squared, right?
Yeah, A squared.
Because it just operates twice.
Yeah.
Right? So this is just 1 plus I over h bar A plus 1 over 2 factorial A squared plus dot dot dot
So
times
just
A.
equal I over H bar A.
Right, this just goes back up into an I can just rewrite this expansion. So it's just I over H bar. I can just replace the eigenvalue there.
Okay, my first instinct was right. I just.
Okay. But beware, this only works for eigenvalues.
Mm-hmm.
If the state here is not an eigenvalue, then it does not work at all. Okay. But there's plenty of times where you're going to use this because, but just remember, it's got to be an eigenvalue. Okay, so let's talk about the spin of the photon then. All right, so for the spin of the photon, you only really have to know, you have to know 2 things. One of them is that you have to know that there are polarizers that can be arranged to block all transmission of light. So everyone's played with this before, I assume, polarizers?
Like sunglasses.
Yeah.
Yeah, those work.
So
You
it's
get two
certain objects-
overlap them.
Certain objects will like produce a prism effect too. Look out with the polarizer, I noticed.
or LCD screens use polarizers. If you take off the LCD polarizer on top, you'll get a white screen. But if you have the polarizer up to your eye, you can see it polarizes the light directly into your eyes only.
Okay, so everyone's kind of played with them. So have you played with taking them perpendicular so that you block out all of the light?
Yeah, forget to take your sunglasses off and now you can't read your phone.
I've seen
Yeah,
demonstrations as well.
Okay, good. So,
We also used them in a Physics 2 experiment. Can't remember, it was a long time ago for me.
Yeah, when I'm wearing these, if my phone is vertical, I can see it. When it's sideways,
But
Okay.
in Physics 2 lab, we used polarizers, but
yeah,
it's
just
possible.
put it on. That should go to black.
It's black.
okay. All right, it works. Experimental proof. Okay, so just a little bit about how light works. These are just conductive polymers, so they're polymers that allow conduction of electrons down the chain, and you just stretch them out to make the polarizers. So that's what polarizers are. And so when if the electric field is oscillating parallel to one of these conductive strands of the polymer, then the electron that's on that polymer is, it's banging against everything as it goes up and down, so it's losing energy. So it just, all of the energy of that light wave gets lost through just, resistance in the polymer chains.
So the light that goes perpendicular retains the most energy, and the more angled it is, the more energy it loses.
Correct. That's why, yeah, right. So if the electric field was polarized perpendicular to those strands, then it gets through, because those electrons can't move and they can't absorb any of the radiant energy of that radiation. Okay, so that's how they work, and so that means that there are two polarizations to the light that you're familiar with. Okay, so we can write the electric field as a vector, say Ex prime and Ey prime, if we call our coordinate system the X prime, Y prime coordinate system.
Now this is the polarization is exploiting the wave nature of light then, though, right? Would you say that? I think you said it was the electromagnetic field. We're talking about the electromagnetic field of the light, right?
Correct, yeah.
Which would be the waveform?
Yeah, I mean, it is a waveform. It's oscillating with some frequency, yeah, and some amplitude. So let's call those polarizations, let's call the linear polarizations X prime and Y prime. So we'll put it in the notation that we're familiar with. And then because we've been dealing with these rotations, right? We talked a lot about rotations for our spin 1/2 system. So let's write our coordinate system. Let's write these linear polarizations in a slightly different rotated coordinate system. So in terms of a rotated XY system. And let's write that then as x is equal to cosine phi x prime minus sine phi y prime, and y is equal to sine phi x prime plus cosine phi y prime. Okay, and so that means if I want to write x prime y prime in terms of xy, that means x prime will be cosine phi x. I think if I'm going the other way, then right? They're in opposite directions with respect to each other, so it's plus sine phi y, and then y prime is minus sine phi x plus cosine phi y. Okay. Okay, now you have to know that there is such a thing as circularly polarized light. Okay, and now we can define states in terms of our linear polarization, but they look like this. Right and left circular polarization. So R will be x plus IY, and left will be x minus IY. Okay, so now let's plug in our equations for x and y, because we want to find what is this in terms of r prime and L prime. So let's plug in these expressions here. So we'll have r is equal to x, which is cosine phi x prime minus sine phi y prime plus I times y, and y is sine phi x prime plus cosine phi y prime. So let's combine our x's x primes. So I've got cosine phi plus I sine phi x prime. And then I've got plus, okay, what do I have here? I've got an I cosine phi, and then I've got a minus sine phi. So I can write this minus as two i's. So I can write this as I times cosine phi, and then minus is I squared. So I can write this as plus I sine phi y prime. Okay, so what is this? This is e to the I phi x prime plus I y prime. Okay, just doing some algebra. But this, our definition here, r was x plus iy, so x prime plus iy prime, this is just r prime. Okay? All right, so we have r is equal to e to the I phi r prime after a rotation by phi. Okay? But the form of the rotation operator, this must be, but the right polarization vector must be the rotation operator by phi. This is some rotation operator on r prime. And so what is the form of this thing? R hat phi has to be equal to e to the minus I over h bar times, it has to be some j hat, some angular momentum operator, times phi on r prime. Okay, we can call this jz. So that's what we were rotating at x and y. So that's a jz. So this means from this result here that we get when we operate on an eigenvector, and you just get back that eigenvalue, this means that jz over h bar operating on r prime is equal to minus 1. Okay, because we just, this e to the I phi is just jz over h bar equals minus 1. So that means that jz on r is equal to, in this particular case, it was minus 1, minus h bar. Okay, so there's a 1 here, right? So for spin 1/2, we had jz operating on z plus gave us h bar over 2 z plus. Right? There's a half here. So this 1 here means it's a spin 1 particle. So the photon is spin 1. Okay? So that's the power. Now, now you know how to calculate the spin of the particle.
The spin 1 means it doesn't spin, right? Or there's only one spin.
Well,
The spin 1/2 means there's 2 possible spins.
There's two spin states for spin 1/2.
Yes. So for one, does that mean there's only one spin state?
No, there's three in general, but a photon is massless, so it only has two spin states. Massless particles only have two spin states. All massless particles.
Is the photon the only massless particle, or are there others?
Hmm?
Is the photon the only massless particle?
No, neutrinos are essentially massless.
They're just nearly massless.
Well, they're for all practical purposes, they're massless. No, there's, other.
Also, there's no anti-photon, right?
Photons are their own antiparticles.
Yeah.
Okay. They're already energy, so I guess.
Hmm?
They're already energy, so I guess the energy. If they combined, they'd just be energy anyway, I think, because they don't have mass.
They can, they're their own antiparticles in the sense that,
They also don't have a charge.
right, they don't have a charge.
Neutrinos also don't have a charge, but there is an anti-neutrino.
Correct.
That's what I thought, because I thought that particles without mass couldn't have an anti, but neutrinos have an anti.
Well, gluons.
No, all particles have antiparticles. Every particle there's an antiparticle for every particle.
So gluons are massless particles too, right?
They're not, these things are called gauge bosons. Gauge bosons are supposed to be massless, but they can, gluons are particles that carry
The color.
they carry color charge. So they're not they gain mass through that.
So they gain mass.
So they gain mass through another process in the standard model.
Okay, I thought that'd be a simple yes or no, but I guess it isn't.
No.
It's yes and no, like everything else.
All particles are supposed to be, essentially massless, and they gain mass through this Higgs mechanism and stuff. So, but the gauge bosons, gauge bosons are supposed to all be massless. But.
So circularly polarized light.
Yeah.
I get it. You got the magnet. So like with linearly polarized light, you got the magnetic field propagating one direction, electric field propagating it perpendicular to that. What's going on with circularly polarized light?
It's changing.
Well, so in a sense, the linear polarization is what's unnatural, because linear polarization is just a mix of left and right polarizations. But the photon itself carries momentum. It carries one unit of angular momentum. So it has to be spinning. It's spinning along its axis. For a single photon has an angular momentum along its axis.
Okay, so is it literally spinning this time, or is it like that, like electron spin where it's not really spinning?
Well, you can't, for a single photon, you wouldn't, it's only classically, you wouldn't get in, so for large numbers of particles, large numbers of photons, then you move into the field description of them, right? So if you have huge numbers of photons, then you can talk about a classical field. And then you can see things like, then you can imagine physical rotation and stuff like that. You can, there's all sorts of really cool electromagnetic effects dealing with this, because there's angular momentum in the field. And, so that can generate, you can generate EMFs and coils and things using, because you have this angular momentum in the field. There's a great, in the Feynman lectures, I can't remember what volume it's in, I think it's in volume 2. And he gives this one particular description of, putting, you put angular momentum into the field, and then he tries to get you to understand, how it can, I can't remember the exact way he phrases it, but anyway, look at